this topic, I show you 7 examples. Yeah. Pretty simple. Yeah. All right. First example. Yeah. Connect PDEs to ODEs. How do we connect? Very simple. Yeah. All right. Main property here. Yeah. So when we understand PDEs, if a PDE involves derivatives with respect to one variable only, yeah, because we only consider the simplest PDE here. Yeah. How simple with respect to one variable only? Okay, yeah, not two. Yeah, two then harder. Yeah, or can be transformed to such a form, yeah, so that the other variables can be treated as parameters. Yeah. Parameters, constant. Yeah. Same thing here. Yeah. Then typically we just solve ODEs. Yeah. Yeah. All right. So the first such example, one very simple one. U sub y equals constant c. C not 0. Yeah. Here we assume U function has 2 variables, x variable and y variable. Yeah. But here you can see, if we treat x variable as a parameter, it's of one variable ODE, right? One variable ODE, yeah, but slightly different. Let's understand this equation as a one variable ODE first. Yeah. 2 variable original function, but we treat x variable as a parameter. All right. Yeah, we can write it this way. Yeah. Parameter A. Yeah. Yeah. Never changes. Yeah. Never changes. Yeah. All right. Then when we take partial derivative with respect to y variable, can we write it as the ordinary derivative, right? Yeah. du over dy, ordinary derivative. So A, we treat it as constant. This ordinary derivative equals constant c. Can we write u parenthesis a comma y, some simple function, antiderivative, yeah, cy plus a constant, but here we should be careful, yeah, because here we do things a little different from our typical ODE case. ODE case, we put a capital C constant, right? Yeah, we put a capital C. When we do antiderivative, yeah, after the main term, we need to add a constant. Yeah, but here, when you add a constant term, you should be careful. Yeah. How do we understand a constant? What's the specific, what is the best understanding of constant here? Because we treat a part, all the terms related to a part, we treat as constant. So when you need to add a constant, general constant part, your new version of constant should contain all the possible a terms. That's the different part. So we need to adapt to the, partial case, partial derivative case. So here we use a general g function. Yeah, g, any function. Yeah. So here, g, arbitrary function. Arbitrary function, it's a function of a. Arbitrary function of a can be treated as a constant here. How about that? Yeah? Because when you take partial derivative, this term is gone, right? When you take partial derivative with respect to y, this term, just like a constant, is gone. Yeah. So now we inverse. We do the inverse on that process. Now we want to get back to the most general constant expression. The general constant expression. So we don't want to use our old way, capital C, too restrictive. Yeah. Capital C, can you treat a capital C as a special case of this G of A? Yeah, include it. G of A contains capital C case, right? Yeah. But your G of A is more general than the capital C case. Because your G of A function, you can contain A terms. Capital C cannot contain A terms, right? Capital C only constant. Only one fixed constant. But your G function can, include many A terms. Other than that part, one constant term, one arbitrary constant term in your G function. All right, so this is our, the solution is quite there. Yeah, solution is quite there. Yeah, but we need to write it because our goal, we want to write our solution as a U function. U of x and y, two variable functions. So we need to go back. So here we use the A as parameter. Now we need to go back to the two variable expression. So the last form should be U of x and y equals cy plus g function of x. G is an arbitrary function. Arbitrary function. Not necessarily differentiable. Okay? Yeah? Because we do not take derivative on G with respect to x, right? Yeah. We do not need to take derivative with respect to x when we want to get the original equation. That's why we do not require G function differentiable. Yeah. Arbitrary. Even if G function is not continuous, it's okay, right? It is a valid function. We can accept it. So that's why we say G function is an arbitrary function. The most general solution. So this is the most general solution. Yeah, that's our first example. Very simple. Yeah. But the special treatment, how do we handle constant? So now you see the first example, how do we handle the constant? Yeah. Because later in many other examples, we need to handle the constant in the same way. Yeah, this way. All right. Example number 2, partial derivative, but second order. So this time, yeah, still with respect to y, but we need to do partial derivative twice equals constant. Yeah. We can treat it as ordinary derivative, yeah, but we do ordinary derivatives twice here. Yeah. All right, because we have the solution of example 1. Can we do the inverse process twice? Okay? The first time, yeah, we use the result of the previous example, but second time we do another inverse process to get the original function u. All right, so let's, yeah, by experience, because this is our experience, right? Yeah, so we can write u partial y function first, right? Yeah. Because we treat this u partial y as a solution of this equation. Can we treat in that way? U partial y as the solution of our example 1 solution. We can write it explicitly by experience because we have this solution. All right. So u sub y of a comma y equals cy and g of a. How about that? But here there is a partial y. Okay? Yeah. There is a partial y here. So you need to do another inverse operation to remove that partial derivative. All right. So the next round, antiderivative, right? Yeah. Ordinary derivative, antiderivative. We know how to do antiderivative on this part. Yeah. All right. Let's write it. All right. U of a comma y, antiderivative with respect to y, 1/2 cy squared, and this antiderivative, we treat this g of a as a constant. Antiderivative g of a times y. We need to add a constant, right? Yeah. We need to add another constant. But this constant, we can have another arbitrary function h of a. Yeah. These two functions are not related. G and h, they are independent functions. Yeah. Independent functions. So we use two different symbols. Well, you see? Yeah. But this is, we treat the first variable as a parameter. Now we need to go back to the x version, right? Yeah. So the final solution version, this is the final solution version. But g and h here could be arbitrary functions. Yeah, arbitrary functions. It's fine. Yeah, but in typical situation in the real world, so we usually we use certain good functions. Yeah, we like to use certain good functions. Yeah, good functions, we like to use g and h as a differentiable functions. Yeah. First, we consider differentiable functions. Yeah. If it's too restrictive, then we go back to continuous function. Yeah. Because if g and h, if we first it should be differentiable. If too restrictive, then we go another step backward. They should be continuous. Too restrictive, add last, ability. All right. So the first two examples. Another two examples in this slide, PDEs with mixed partials. Yeah. Partial x, partial y, mixed partials. Yeah. All right. Number 3, yeah, let's solve this one. U partial x, partial y equals c. Yeah. So similar to our first example, yeah, but this time we need to do inverse process twice with respect to two different variables. Y once, x another time. Yeah. So here when we do it twice with respect to different variables, when we work on constant part, we have to be careful. Because we need to write a constant form. Yeah. Yeah. So pay attention to the constant part. All right. First, yeah, we can, separate. Yeah. Two partial derivatives, let's separate them. Yeah. First, let's consider its partial x. Okay? Yeah. Partial y. Yeah. First, then we use our example 1 solution. Yeah. This is, for the example 1, we have the solution. Can we use the solution form of example 1 to write partial u over partial x? Yeah. Because partial u over partial x corresponds to the solution of example 1, right? Yeah. Yeah. U sub x corresponds to the solution of our example 1. All right. So let's write it first. U sub x equals cy plus g of x. Here, g is an arbitrary function. Yeah. Easy? All right. Then, now we need to antiderivative with respect to x variable this time. X variable. All right. Now we should be careful. When we write out the constant part, there is a constant part. We should be careful. All right. So u, xy variable, original u function, antiderivative, this term, with respect to x variable, cxy. That's cxy. Then this part antiderivative integral of g function form. Okay? G function. Yeah. All right. Now, before we go to the next step, remember, in this step, we only require g function, arbitrary function, right? Yeah. But when you write this integral form, do you want to modify the g function a little bit? Because if you put arbitrary function there, you may have problem, right? Yeah, think about it. In this expression, if you only require g function is an arbitrary function, do you have some problem? Think about it. Yeah, you have some problem. Because the integral may not be well defined. How do you know you can calculate the integral successfully? Because the integral may not be well defined. The integral may not exist. Think about that. If g function is very bad, people can create a, very radical, function. Yeah. Then, when you do the integral, it does not exist. Yeah. So we need to modify, because we want the minimum condition, we want the integral exists, right? Yeah. So here we need to modify. G should not be arbitrary function. G should be integrable function. There is an integrable concept. Yeah. The integral definition, there is a limit, right? Yeah. So you go back to calculus. We use limit to calculate the integral. How do you know the limit exists or not, right? Yeah. The limit may not exist. Yeah. Integrable, then the limit exists. the limit converges. Yeah, integrable. Yeah.
Is that a real word? Did you make that one integrable? I've never heard that word.
Oh, never heard of it. But in calculus, it's very popular. Yeah, very popular. Integrable. Yeah, the function must be integrable. Yeah. Okay. Yeah. So that's a valid concept. Yeah. Valid concept. Yeah. All right. Yeah. Now, are we satisfied? So this, if this is the final solution, are we satisfied with it? Yeah. Yeah. Still, yeah. We need to, because when we write in this form, the constant part is still hidden a little bit, right? Yeah. Because when you take this indefinite integral, there is some hidden constant part. Yeah. Remember constant c? People need to add that constant c. How do you write that c part? C, remember, we treat x or y as constant, right? Yeah. Because when you write c, how do you want to include x or y in your c? That's the question. You don't understand, right? Yeah. So let me explain. Yeah, this part is a little hard to understand. So I need to explain this, the constant part. What is the appropriate constant part? Because here hidden, okay? Hidden. So we need to reveal the hidden constant part. Yeah. All right. Let's look at get it here. Okay. All right. Yeah. U function, you take partial x, then partial y. Can you switch the order? You take partial y first, then partial x second, right? Yeah. The order doesn't matter, right? Yeah. Now, if we switch the order, okay, that means we can write, do the similar things. Yeah. Uxy equals cx plus hy. Okay. Yeah, because use a different variable, okay, different version. If we use this version, then we do this, similar inverse step. Then cxy, here, the same. But this part, we have integral of h of y dy. Yeah. So here, gh, yeah. You can see two different forms, but these two should be the same, right? Because here, left-hand side, the same u function. Right-hand side, the forms are different. Yeah. How do we write the update of the new form that covers both cases? Now, yeah, because both correct. Yeah, both correct. Now we want to write our final solution form, but the final solution form should cover both cases. Cover both cases. All right. So let me write it out. Okay. The final form, yeah, because the cxy, this is the common term. We keep the common term. These two terms look different. All right. Antiderivative, we can use a capital G function. Antiderivative, it's another function, right? Can we call that whole function integral of little g function as a capital G function? And the capital G function this time should be differentiable. Can you see capital G function must be differentiable? Because its derivative is little g function, right? So capital G function must be differentiable. Because you can take derivative of capital G function. You get little g function. Similarly, capital H function antiderivative, this integral. So capital H function must be differentiable also. Okay? Yeah. You have, so your final form should be this form with differentiable capital G function and a differentiable capital H function. That's the final form. Now you go back to check. You use the final form to check these two. Yeah, both correct. Let me tell you. Yeah. Why? When you look from the, outside form, they look different. They're different. But actually, you can, based on our understanding of partial derivatives, this final form covers first one, also covers second one. Yeah. Now, why this one covers the first one? Yeah. Look at G of X, capital G of X covers this term, no problem, right? But the capital H one, can we treat, because there is a hidden constant, right? So capital H in the first version, it corresponds to some hidden constant. Yeah, there is a hidden constant. Capital H function, capital H of Y, we treat it as constant, right? Yeah. So that capital H corresponds to constant term in the first version. Similarly, for the second version, capital H corresponds to that one, but the capital G function corresponds to a hidden constant term. Yeah.
Depending on which derivative you took first.
Right. Yeah. Because, which derivative? Yeah. So that's the, a little tricky part. Yeah, because our understanding, when we switch our mind from ordinary derivatives to partial derivatives, we need to do some special adjustment here regarding the constant. Yeah. Constant, our understanding of constant is different from our old way. Old way constant is constant. Yeah. But here, constant may involve some variables, but variable we treat as parameters. When we call parameters, we do not treat them as variables, right? Yeah. That's the part you need to be very careful when you work on the partial derivatives. Okay, yeah. All right, let's look at some more examples. What question?
Yeah, I was going to ask. So, I guess, we work on these two things separately, and then at the end we combine them, right?
Yes.
But CXY is going to, we're basically just taking what we need from each and then
Yes.
putting it into one. So it wouldn't be CXY squared or whatever.
No. CXY appears in both versions, right? That's the common terms we just copy.
Yeah, we're just grabbing it.
Yeah, grab, copy.
Okay.
Yeah. Do not change anything, okay? Do not square, do not change. Yeah. Copy those common terms. But different part, we need to, use a big umbrella to cover both. Yeah. Big umbrella to cover both. Yeah. Later, we have some situations. Yeah. So later, when we work on some special examples, we need to use this understanding. Yeah. All right. Yeah. Number 4, mixed. Yeah, but here, part U sub X. Yeah. This one. Yeah. Let's solve it. Yeah. Using the ODE way. Yeah. ODE way. Yeah. Because if we treat U sub X as one function, is that ODE? Yeah. Our first step, let us write U sub X as another function, V function. V of xy equals this partial u over partial x function. Yeah. If we introduce a new variable v function, new function, v function, yeah. So original equation we can write as v sub y equals v. That's ordinary ODE. ODE. And we know how to solve it. We did it before. Do you still remember? We solved this ODE sometime before. We did it. Think about in our first class. We did it in our first class. First class, part A. Part A, yeah. Let me did we solve this in our first class? Y prime equals y. Because we tried to find a special function, its derivative equals itself. Did we do that? Some function whose derivative equals itself. E function, right? Yeah, E function. Yeah. So our solution is a times e to the t. Remember? Y of t. A times e to the t. Yeah. Yeah, but here we do not use t as variable. Yeah. So we should change t to x. Yeah. T to x. V of x comma y equals a function. Yeah. Because here we treat x as parameter, right? Yeah. So our a part, we should include x. A is a function of x. Okay? Yeah. So when then e to the y. Y is the variable. Y corresponds to t here. Y is the variable. Constant part, you should include. It's a function of x. Yeah. All right. That's the first step. First step. Then u sub x equals a of x function times e to the y. How to get antiderivative here. Yeah. Integral, right? Integral, yeah. U of xy, yeah. Antiderivative, e to the y times integral of a of x plus some appropriate constant term. Yeah. Yeah, but here x is the variable. So this constant term should contain certain function of y, right? Yeah, because we treat y as the constant parameter. Yeah. B of y, capital B of y. This function we can use capital A of x, represent that function. Okay, so then this function capital B of y function. That's the solution. Yeah. A and B differentiable functions. Yeah. A differentiable, B we may not need a differentiable, right? Yeah. So here, yeah, B may not be differentiable, yeah, but ideally, yeah, we may like a differentiable. If there is a problem, then we modify B. Yeah, if differentiable, there is some difficulty there, then we can make it a continuous function. If still does not work, then we consider arbitrary function. Yeah. But if the differentiable function make it work, then we like to have a differentiable function, right? Yeah. All right. Number 5. All right. This time, yeah, a little harder than the previous one. Yeah. But here, we need to solve a second order ODE. This is second order ODE, right? Yeah. If you can solve second order ODE, then you can write that solution in a similar way. Yeah. So what is the solution of this second order ODE? Yeah. Yeah. Here, recall. Yeah. I think you solved this kind of ODE before, right? Characteristic equation, lambda squared minus 1 equals 0. You first write its corresponding characteristic equation. Okay? Y double prime, its characteristic equation, you use some variable. So many people use lambda, yeah, or some other people use different variable here. Lambda squared minus 1. Two solutions, lambda equals 1 and a negative 1. Solving this algebraic equation. Then you can write solution using these two roots immediately. Solution y of t equals capital A constant times e to the first lambda times t. Yeah. Okay? Capital B times e to the second lambda value times t. That's the solution. Yeah. Yeah. Later in our module 2, when we work on second order ODE, we will get to this topic another time. Yeah. Another time. Yeah. So here, because this equation is very simple, I'll just show you it. In our module 2, when I talk about characteristic equation, I will explain why characteristic equation will give us the solution of the original equation. Yeah. I will explain that. Module 2. Yeah. All right. Then, now, because you can write the solution of this ordinary equation, when we move here, we need to do adaptation, right? Yeah. Adapt to, yeah, because this two variable case. So we need to write this equation containing both x variable and a y variable. All right. So when we write it, a constant, now we use capital A of x function. Because x we treat it as a parameter. So that should be inside capital A as a variable of the function. Then e to the y. Then capital B of x times e to the negative y. Yeah. All right, yeah. Capital A, capital B, arbitrary functions. Yeah. All right. Yeah, that's example number 5. Number 6, similar example. Number 6, change minus to plus. Minus to plus. Okay, all right. Then the same method. We solve y double prime plus y equals 0. Second order ODE. Then we need to solve the corresponding characteristic equation. Lambda squared plus 1 equals 0. It has two roots, I and a negative I. Yeah, because this time the solution, not real numbers. We need to use imaginary numbers, I and a negative y. Okay, yeah, so then when we write the solution, negative 1, we can write capital A times cosine of t plus capital B times sine of t. Why cosine? So sine. because we can use Euler's formula, e to the it equals cosine of t plus I times sine of t. That's the Euler's formula. Okay? Then, because so let me write an intermediate step. Before you write this is the final step. Before you write this final step, you may write an intermediate step, should be e to the it plus b plus e to the negative it. Okay? If we use the similar way, e to the it, okay? All right. So that's this form. This form, then you can apply Euler's formula, right? You can apply Euler's formula. Okay? Yeah. And then when you apply it, a question? Yeah?
Yeah, I was going to ask where the I before your sign goes in the equation we just read above it. Do I miss that?
Yeah.
Because it's cosine.
Yeah. Right. Yeah. So, okay. Yeah. And then A, we can write, apply Euler's formula, t plus I sine t. And plus B cosine minus I sine t, right? Yeah, okay with this one, right? Apply Euler's formula. Yeah. Then, can we combine the terms, right? Yeah, combine the terms. When we combine the terms, A plus B cosine of t plus I A minus B sine of t, right? Okay? Yeah. All right. When we have this form, can you see, you can simplify, you can simplify to this AB form. Yeah. AB, remember, arbitrary constant. Arbitrary constant, we have freedom to choose appropriate AB form, and at the end, we can simplify to this, because we want to remove I. Think about it. We want to remove I. Okay? All right. Yeah, but let me give you a few steps of manipulation. A few steps of manipulation. All right. First, can we assume A equals B first? A equals B. Yeah? Because arbitrary, we have freedom to choose special AB, right? Let us choose capital A, capital B, the same. When we choose capital A, is this term gone? That term gone, right? Okay? All right. So 2A cosine t. 2A cosine t. So do you feel okay 2A cosine t is a valid solution? No? Yeah, no problem, right? Okay, all right. Then, next round, can I assume A equals negative B? When I assume A equals negative B, is this first cosine term is gone? Right? Cosine term is gone, but I have the second one. Second part, I have negative 2I B sine t, right? In this B, can I make B contains another I? B equals I B0. Can I assume? Because B arbitrary constant. Now I take B equals I times 0. So I have I here, another I, I times I, negative 1, right? So I have 2B0 sine t. I have another solution, 2B0 sine t. another solution, right? So we have two solutions. One solution here, another solution here. Then the sum of the two solutions, is it another solution? Because this equation is a linear equation. It has the linearity property. Linearity property. Linearity, that means we have two solutions. Then we add up these two solutions. It's another solution. Then add up. Do we have the solution? Yeah. Because 2a, yeah, we put together, we treat it as a new constant. Arbitrary constant. Yeah. Yeah. Because this version does not contain I. It's more friendly, right? Yeah. So we want to avoid I in our final solution. More friendly. Yeah. But you can see we do a lot of manipulation steps. All right. So let's take a break.